okay? And this handle can actually shrink to 0, but it's still rotating. And it's very important to think about it. It rotates with a uniform speed. So even if they shrink to 0, it's still rotating. It's an in-string rotation in this point. And that means the value will be 0 over here. So we could create a lot of different things. And then we can have a situation where I'm going to use another color for this. Well, I thought I had a red pencil here, but obviously it's gone, so it doesn't matter. But the thing is, like this could change smoothly position in an orbit like this, over time. While it rotates, the handle gets shorter and shorter and shorter and shorter until it comes in here. And that's so if we say it was on top here now, and then it's going down to here, that means we will have something like this. So it's a smooth transition. And we can of course continue these transitions all the way to 0. Like this. In other words, what I'm saying is we can have a value that over time change like this. That's clear? Okay. I'm just going to point this out now. I'm not going to say that this is the energy, because it's not, but I want to point out that the outline we have here, this outline here, is also a wave. It's a wave on top of the wave. I want you to keep that in mind, that we have a wave on top of the wave. More precisely, the area increase well, the area increase the square, the radius. So if the radius is 2, you square this and you get 4. So it's 2 times 2, 4. If the radius increase from 2 to 4, then the area increase from, which is 4 here, from 4 to 4 times 4, which is 16. And that means the area is increasing much more rapidly than the radius is doing. So when this handle is growing in length, the rate at which that handle is growing in length is much less than the area the handle is covering is the area of the circle the handle creates grows much, much faster, and this is called an exponential growth. And we can represent that exponential growth with so this here now is our y position and x position. And then we have our handle that is like some length along the x line. Here, let's say it has this length. And that can then that length of the handle can in itself be interpreted translated into a shape like this. I don't think it looks good here, but actually what I'm having here is a bowl, and that's the y, and then we have the x-axis here, and then we have a z-axis, the z-axis. And so this is in the plane where the handle is, in the xy plane where the handle is rotating like this. And that I said that because of this relation between the area and radius, if you make that function of the length of the radius and plot it along a z-axis like this, then that value for this particular length will end up here. If we make this arm a little bit longer to over here, then this value, the z value, that relation between the area and the length of the length of the radius, that value will end up here. And if we shorten it, the value will end up somewhere here. And when we do all this, it will end up like this bowl shape in space. Now, so we could read off a value there, which is a set value, which is a function of the length of the handle that rotates. And that set value I'm going to call energy. So what I said before is the height of this wave here, that's the length of the arm here, or other words, the max value here is when this handle is pointing straight up in the y direction, and that value there is the length of the arm, okay? And that means this peaks here, or this outline here, is the length of the arm. and here is the arm or handle. It's shrinking, and here the handle is increasing in length, shrinking, increasing, shrinking, increasing, shrinking. Okay? And that behavior can then be translated into energy. But this is not the energy. The energy, if because energy, like you see, this value is also negative here. It has this thing. So when we talk about the energy, we're only thinking about that top half there, that length of the arm. And I don't have much space. Maybe I could write it here. So the energy here will correspond to a similar shape as this. So the energy here would be like, no, I have to little space. I'm going to do this on another paper. So okay, I've made a new sketch here now. So if this is the length of the arm here, and this is time, and this is the Y position here. No, this is set, and this is time. And then we look at this thing here. This means that if we have that rotation, we have a fixed length of the arm. So it just goes in a fixed curve like this. So it's the same all the time. That means the energy, or that value, is going to be a straight line like this. Now, if we have this case, what that means is that we first have a rotation inside here, and then it decides to go out to an outer circle like this. This is what the rotation shows. And this is the set value will then go like this. It will kind of like follow that shape here, because it's related to the length of the handle. And then we could have, like I said, the values can change. So it can go in this case we have a mean and we have a max like this, and then it goes up to the max, and then it goes down to the mean, and then it goes back up to the max, and then it goes down to the mean, and that will create a shape like this. And the set value will then change like this. And notice over here is 0. This mean value here is a negative value, but it's only related to the length of the arm, and the length of the arm can actually is the mean value here in this case, since it crosses the 0 line, is back to the pointer. But if this is 0, otherwise, if this would be, let's say, 1 here, this would be 1, not 0. So that's a little mistake of mine. And this is over time, and this is how set, or what I said was the energy, vary over time. It goes up and down and up and down and up and down. Now, do I have time? No, I don't have more time here. But in the next video, I will relate back this to the field. So if we come back to the field now, all these exercises I've just gone through was just to explain how a value can change in a field. And